Hey everyone, welcome back for Module 5 of the CompTIA A course. Today's module is titled Installing, Configuring and Troubleshooting Internal System Components. Now some of the main topics we're going to be taking a look at today is installing and upgrading CPUs, configuring and upgrading BIOS or UEFI, depending on how new your motherboard obviously is, installing power supplies, also known as PSUs, power supply units, troubleshooting internal system components, and lastly, configuring and building a custom PC. That could be something like a gaming PC, maybe a home entertainment system. I think you guys get the idea. So now that we have got an idea of what the topics for this module is, you guys know what to do. Give the video a like, it really does support my channel. If you're new to my channel, welcome. Maybe consider subscribing down below, especially if you would like to know when the next video for this series comes out or any of my other videos. So preferably the notification bell, otherwise you're only going to see it when it's too late. And I think now that we've got all these topics out of the way, let's jump in and go have some fun. Alright everyone, here is our first topic for this module, being CPU. In case you guys haven't guessed it already, that's an abbreviation for Central Processing Unit. It's called Central Processing Unit because, believe it or not, this chip, which is an actual chip, used to be in the center of your motherboard a long time ago, many moons ago. Nowadays, on the average motherboard, that chip is still a chip, but it's more towards the middle at the top of the motherboard. So I suppose, in a manner of speaking, we could actually technically call this the TPU for top processing unit, not the central processing unit. It is still, however, the main brains of your computer. This is where all the calculations and functions gets done. Well, for the most part, at least. It controls all of your I/O functions, being your input and output functions, processes simple instructions quickly. How quickly? Well, that depends on quite a few things. First of all, it depends on your clock speed, something we are actually going to take a look at in this specific module. So depending on how quick your clock speed is, that'll determine how quickly it calculates things. It also depends on your CPU's cache, also a topic covered in this module. CPU cache is basically a form of memory, temporary memory if you will, that's built physically into the CPU chip. The bigger the cache, the more your CPU is going to cost you. The bigger the cache, the less information your CPU has to send to the RAM. Now, as you guys would remember from the previous modules being the storage module, RAM is what gets loaded from the hard drive into the RAM. So whenever you want to launch a game or a program or whatever it is you're working with on your computer, it's going to take that program or whatever it is from your hard drive, load it into the RAM because that's a very quick form of memory, much quicker and faster than your hard drive. And then from the RAM, between the RAM and the CPU, it's going to basically hand it to the CPU zigzag. You can think of the RAM as your work desk. It's a desk that you're working on, and everything that you're working on at that point in time will be lying on that desk. So if you're working on a certain document, that document, all the pages will be lying on that desk. You might have hundreds of documents, but the ones you're not working on might very well be stored in a cabinet or a file cabinet somewhere. And one day when you need that file, you're going to go to the file cabinet, take it out of the cabinet, and put it on your desk so you can work on it. Now that disk is your RAM. The file cabinet, in case you guys haven't made the assumption yet, is your hard drive. So even though your RAM is very fast memory, it still has its limits. So on the motherboard, it's actually light years away from the CPU. To you as a human being, it might not seem like a big deal. It might look like it's half a hand's length away from the CPU chip. But in reality, that is a very long path for the data to travel between the RAM and a CPU. Zigzag, that's just light years. So the more cache your CPU has, the more information it can store regularly in the CPU. That is less information that needs to go out to the RAM. So anything that gets calculated very regularly or that gets used very regularly, that gets stored in the CPU's cache. So that's less information that needs to go and pull all the way from the RAM and back and forth because it's stored locally. It's just going to make it quicker. Alright, and then we obviously have cache, which we've kind of already accidentally explained. So like I've said, cache is a form of memory. Now the word cache is something you guys are going to hear in IT quite a lot. It's generally some form of memory, not always CPU memory though. In today's topic, it's obviously CPU memory. So you get, for example, browser cache, you get branch cache, and then you obviously get CPU cache. One way or another, cache is generally some form of temporary memory which stores something that you or someone or something uses quite regularly. And what they all have in common, never mind them being memory, is they're used to speed things up. So with regards to CPU, like we've just said, that's a small piece of memory built physically into the CPU chip. And what you would notice is if you go look at the prices of CPUs, do yourself a favor, go check online the prices of CPUs. One of the things that basically determines the price the most is the cache. You might very well find yourself a CPU that's got a clock speed of 2.5 gigahertz. Maybe you'll find two of them that's 2.5 gigahertz. The one will cost $1,000, the next one might cost you $2,000. And what determines that price is not just the clock speed, it is the cache. The one might have a 2 megabyte cache, the other one might have a 4 megabyte cache, or even so on and so forth. So the bigger the cache, the more you pay for it. That is in most cases the biggest price deciding factor, is not the clock speed, it is the cache. So you're actually paying for the memory inside of the CPU and not so much for the CPU itself. All right, everyone, let's talk about hyper-threading. So Intel's hyper-threading technology has been on their computer processors for close to about 20 years now, I think. At least at the time of the making of this video, it was close to about 20 years. And yet, most people don't know anything about it or know very little about what it actually is and what it actually does. So let me start things off by giving you an analogy of what hyperthreading actually is. Let's say I'm a CPU. Yes, me. I'm a CPU. And I'm trying to process food. Or as some people might say, eat. I'm trying to eat food. I can only do as much eating as one mouth can do. Now, if I could add more mouths, I could process more. In other words, eat more. Now, that is what multi-core processors do. So if I have one mouth, that's one core. If I have two mouths, that's two cores. The more mouths you have, the more you can process, the more you can eat, in other words. So when you have more cores, you can think of it as, well, having more mouths that you can eat with. Now, unfortunately, due to cost constraints, among other things, it's not always possible to take that approach, though. So, I have just one mouth, which you can think of as a single core. So, how can I get that faster, in a matter of speaking, without giving it more mouths? I can use my hand to pick up the food, bring it to my mouth, then grab another bite while my mouth is busy. Now, something I want you guys to think about though is if I finish chewing before my hand is ready to deliver me more food, however, my mouth is effectively just sitting there doing nothing. Now, if only I could use two hands to prepare food for my mouth, then even though my mouth can't actually work any faster or eat any faster, if you want to go and call it that, I wouldn't waste any time. Oh wait, I can do that. That's hyperfitting. So you can think of it as having one mouth, but more than one hand that can feed it. So if the one hand is not ready yet to provide my mouth with more food, the other hand can provide my mouth with food. So you can think of it as using both your hands to feed your mouth. So your mouth is not just sitting there at any point in time doing nothing. It's constantly doing things. So it's effectively not wasting time. You're using time smartly. So in other words, it's one processor and intelligent scheduling to make sure that it's always working. That's pretty awesome, right? Well, usually. Hyperthreading can't do much for single-threaded workloads where you can only work on one thing at a time. For example, if you wanted to eat a 2-scoop ice cream cone, you can't work on the bottom scoop until the top scoop has already been consumed. With that example, there is no benefit to adding more mouths or more hands. In other words, more cores or more hyperthreading. So if you're going to go and add more cores or more hyperthreading, no benefit. Now the opposite of this would be eating from a bowl of candies, which are all kinds of colors. Now, grabbing and eating a red candy does not in any way depend on finishing the blue candy that's already in my mouth, perhaps. In fact, if I have some friends to help me eat it, we could consume the candy very quickly by adding more hands and more mouths. This is an example of multi-threaded workload, and hyper-threading can definitely help with this. Alright, so let's bring it away from the eating analogy for a minute and bring it back to the real world. Competing tasks that benefit from hyper-threading and multi-processing cores are video editing, 3D rendering, and heavy multitasking on your PC. Okay, so yeah, I think that pretty much gives you guys a good idea of what hyperthreading is and what it does. Okay guys, so next up is clock speed. This is actually also sometimes referred to as clock rate or clock frequency, in case you've ever heard of those terms. Now the clock speed, which is these days measured in gigahertz, is basically an utterly meaningless metric these days and has been pretty much for the last 10 years. First off, speed in megahertz or gigahertz measures how many clock cycles a CPU goes through each second, and a cycle is basically what happens when an electrical pulse hits your CPU, allowing it to execute instructions and keep its activity in sync with the rest of your system. So this means that a processor rated at 3 GHz can handle a billion more cycles per second than one rated at 2 GHz. Now that's simple enough to understand, but things get more complicated when you consider what happens during a clock cycle. One big determining factor of a CPU's performance is how many instructions that it can execute per clock cycle. Modern processors can work on more than one instruction at a time. This is thanks to pipelining, which you can think of as being similar to how an electronics factory can turn out a huge number of smartphones per day, even though it might take a long time for one phone to make it all the way through the assembly line. So different stages of production are pipelined to take place simultaneously so that the guy that installs the screen isn't constantly sitting waiting around for the next phone to work on. Pipelining in CPUs is similar in principle, but quite a bit more complicated, and engineers use different methods to allow the processor to chop instructions into parts that can be worked on simultaneously or even combine smaller operations to complete them in fewer cycles, increasing efficiency. Now, exactly how this gets accomplished depends on the specific microarchitecture of the processor. This basically means that because of the number of instructions per clock cycle and the pipelining efficiency can vary, obviously enormously between CPU brands and the individual models from a single brand or clock, at the end of the day, it's very hard to determine these days. So in a nutshell, clock speed can end up being very, very deceiving. So what I actually want to say here is don't just look at the clock speed these days. So if you're going to go and buy yourself a CPU, one CPU might have a clock speed of 3 gigahertz, the next one has the same speed, but in reality the one is actually much, much faster or much, much more efficient due to other kinds of variables. Variables like the microarchitecture, how much cache it has, all kinds of things like that. Alright guys, let's take a look at our next topic being overclocking. Now, the previous topic was clock speed or clock rates or clock frequency. This one is overclocking. Not exactly the same thing, but I suppose you can throw it in the same ballpark in a matter of speaking. So overclocking is when you're going to basically go and speed up the processor. This can be done via many ways, but it generally involves you going into your firmware and all that, and changing the multipliers and all that in a nutshell. And what's going to happen is you're going to be sending more power to your CPU. More power means more speed. More power also means more heat. So generally, when CPUs are made, they're tried and tested by the manufacturer, and they're obviously pre-configured to a certain speed. Now, if you're going to go and overclock it, you're pushing it beyond its manufacturer limits. So it wasn't designed to go and run at those speeds. You can think of this as the same as a car that you're constantly driving in the red. So you're supposed to be driving it at normal revolutions per minute. And if you can be driving that car constantly in the red, it might not fail immediately. It might not be tomorrow. It might not even be next week. But what's going to happen here is you're drastically shortening that car's engine lifespan. The same can be said about a CPU. They were generally not designed to be running at those high clock speeds. So sure, you're going to get a little bit more performance out of it, just like that car engine, for an X amount of time, but its lifespan might have originally have been 5 years, where now it might only last you a mere 3 months or 6 months. Never mind the heat problem. Like we said earlier, if you're going to be sending more power to a CPU, you're sending more heat to that CPU. So if you want to do that, you need to know what you're doing when it comes to cooling. The normal conventional heatsink and fan that you have on your CPU might no longer cut it. You might need to consider getting yourself a better fan, better heatsink, or better yet, maybe liquid cooling. So all in all, guys, it is not something I would recommend unless you absolutely know what you're doing. It is definitely not something I recommend you try. So know what it is. That obviously means you're overpowering your CPU. You're giving it more performance, but you're giving it more heat. But don't try this on your own. And then we have what is referred to as throttling. As you can see, technology that allows the CPU to slow down if the thermal output reaches a critical level or to improve power performance. So it can be for more than one reason. The more common one you're probably going to see is power management. Most computers, especially laptops, have power options. So by default, a laptop has a power option which says recommended, which means when you need performance, it'll give your CPU more power. More power means more heat and more performance, like we previously said. Now, when you're not using your computer for whatever tasks, it's going to reduce the power sent to your CPU because it's obviously just idling there. It's not being used for anything. So it's not being used really for anything. Why not reduce the power sent to it? Because that now means you're going to be using less power. Your power bill is going to obviously be much lighter. It's also very efficient on a laptop, which might potentially be running on battery power and not off the wall socket. If you're running on battery power, you obviously want to try and stretch your battery life as much as you possibly can, which is why we go and choose the recommended power option, or better yet, power saver. There's an option you can go and choose which is called power saver. You can even go and create your own custom power plans, which basically runs your computer or your CPU in a low power state. So you're sending less power to your CPU, less heat, less battery life is consumed. The downside, because there's always a downside, is you're going to have less performance. So if it's something like a laptop, you're going to notice a drastic reduce in performance. So also where this might possibly be used is when your computer will automatically go and slow down the CPU or the power sent to it because it detects that your CPU is running too hot. So it's basically a safety precaution built in by most manufacturers these days. If your computer detects that the CPU is running too hot, it'll either slow down the CPU, in other words, send less power to it, or in some cases, maybe even turn off your computer. This is actually a very real issue you guys are going to face quite commonly with your clients or your users, where a client might say, I started my computer, it was running fine, and it just randomly shut down on me. And when I try and start the PC back up immediately afterwards, it fails to start. It just doesn't want to start. And if I wait about 5 or 10 minutes or half an hour, then it magically starts again for about 5 or 10 minutes. And it turns itself back off again, and then it just doesn't want to start again. That is a sign of an overheating CPU. It can be for many reasons, the most common reason being the thermal compound, which is also known as heat-based, might have dried out. So the CPU is not getting proper cooling. Could be that the CPU fan is maybe faulty, maybe there's a lot of dust in it, the heatsink is loose, maybe the thermal compound being heat-based that's between the heatsink and the CPU is dried out or there is none. All of these can be indicators of a CPU that's overheating. Alright guys, so let's take a bit of a look at CPU packaging and CPU compatibility. Now if you are going to go and build yourself a PC or a PC for a client or a user of some kind, I suppose it's really up to you in the end of the day where you want to start, but my personal preference is to start with the CPU I want. So if I want to buy myself, for argument's sake, an i7 CPU, obviously there's many on the market. You go and choose the i7 you want, and you go and check what socket that is. So you can say, and you see in this case, they've got a socket Intel 1150 there. Now the socket number is the amount of pins your CPU chip has underneath it, or contact points if you will. Sometimes the actual pins are underneath the CPU chip itself, and those pins basically just slide into the motherboard. The other times you might find the pins are on the motherboard end, and the contact points which the pins need to connect to or make contact with are on the bottom of the CPU. It's a vice versa kind of situation. It depends on how old the motherboard and CPU is. It also depends on what brand of CPU we're talking about. Are we talking Intel or are we talking AMD? Now, generally at this point in time, how things stand is with Intel, The contact points being the pins, the actual pins are normally on the motherboard, where on the CPU you'll just find little copper contact points. And on the other hand, with AMD, the pins are still for the most part on the CPU side, and the contact points where the pins need to make contact with, that is on the motherboard side. I suppose it doesn't really matter where the contact points are at the end of the day, but my personal preference is to have the actual pins themselves on the motherboard. Generally, in most cases, you'll find that the motherboard is very expensive, the CPU is very expensive, but if you have to do a comparison, on average, your CPU chip will be normally way more expensive than your motherboard. So if you were to, hypothetically speaking, make a boo-boo and bend one of those many pins, where in this case it's 1150 pins, if you were to break one of those pins or bend them, and yes, it's very easy to bend or break one of them, you preferably want to bend or break the pin on the item that's cheaper to replace, which is usually the motherboard. So I like the fact that Intel has made the pins on the motherboard in, because that is the cheaper one of the two components in most cases. So if I lose the motherboard, I'm going to be a lot happier than losing the CPU. Obviously, you're not going to be happy if you lose either one of the two, but still, it's cheaper. On the AMD side of things, which we're going to get to in just a second, the pins are unfortunately on the more expensive of the two items. So if you're going to lose a pin, you're going to have to replace the CPU in that case, which is the more expensive one out of the two. In regards to Intel, you can see they've got a few examples there of which what you get. It's obviously not limited to just that. LGA simply just stands for land grid array. So that basically just means where the pins are. So land grid array is what Intel uses for the most part, which means the pins are on the motherboard. You can think of the motherboard as the land. So the motherboard is the land, it has the pins, land grid array. The CPU just has the contact points. Where an AMD CPU is pin grid array. That one is the opposite. We call that PGA. Instead of LGA, it's PGA. Now, back in the day, many moons ago, Intel actually had PGA chips as well. So thank God they've moved away from that. Here we have ourselves an AMD setup. So you can see that's an AMD motherboard, probably a very old looking one. Although I see it does mention DDR3 there. So you can see there is another socket type you get there. It's obviously not just limited to those kinds of sockets. You get many kinds of sockets on both the Intel side as well as the AMD side. So if you're going to go buy yourself a CPU, whether it be for AMD or Intel, buy the CPU. Once you've established the pins or the socket size of that CPU, then you can go hunting for a motherboard. A motherboard that supports that socket size of that AMD or that CPU, and it also supports that speed. Just because that CPU fits into that motherboard does not necessarily mean it's compatible. You want to make sure that it's got the same speed. That motherboard might very well be too slow or too fast. Probably too slow for your CPU. Alright, boys and girls, and then we've got cooling mechanisms. Now, what we've got here in the course is absolutely not the only way you can go about cooling your machine. This is probably going to be a gaming rig. It's not limited to gaming, but let's imagine this is a gaming rig. So you've got your heatsink. That's pretty much the most common thing you get. It's a passive heat exchanger. It's a passive cooling device. So the word passive means it's a way of cooling down your CPU or your computer without using any form of electricity. So heat sinks are normally made out of metal, more specifically aluminium. They absorb heat very well, and yet they stay cool. So if you go check your CPU, you would normally find that that piece of metal you go and connect to your CPU. It's got like four little clips that you connect to your CPU. That piece of metal, which is normally chrome in color, that is a heatsink. That's aluminium. And on top of that heatsink, in most cases, you will have a fan which cools down the heatsink even more. Even though it doesn't really need that in some cases, it cools down the heatsink even more. Then we have what they call thermal paste. This is also sometimes called thermal compound. It looks like toothpaste in some cases. It might actually be white. Although these days I've seen some of them actually be gray in color. I suppose it could technically be any color, but usually it's either white or gray in color. It comes in like little syringes. Sometimes you'll get them in huge tubes, like an actual toothpaste tube. And the idea is when you put your CPU into its little socket on the motherboard, you want to go and put a small little amount on top of the CPU, preferably in the middle. I would say basically the size of your pinky nail. So you put that small amount, the size of your pinky nail, on the CPU, just rub it in a small little circular format, and then you can go and mount the heatsink on top of that CPU. So what this is going to do is it's going to allow the heat to transfer just so much better to that heatsink. It's not that it's not going to transfer at all. It probably would have transferred a little bit to the heatsink, but not as much as you would like. So the thermal compound is just going to transfer the heat a lot better. It's a very good heat conductor. It allows it to transfer the heat. If you're going to go and buy yourself a brand new CPU, most of them you'll find actually comes with a heatsink included. And that heatsink and that fan, yeah, I actually forgot to mention there's also a fan included normally. That heatsink and fan is designed for that CPU, and they normally actually have heatsink pre-applied to the bottom of that heatsink, which is pretty cool. So you can just literally go and mount that heatsink in that CPU and you're all set. At the bottom, they obviously mention passive cooling again, and we know what that is. That's a form of cooling that doesn't need electricity. Here's another type of cooling you get. You get liquid cooling. This is generally something that you only find gamers go and use. I suppose it's not just limited to gamers, but for the most part, gamers are the ones that most popularly like to go and use what we call liquid cooling. So obviously, instead of having a fan and a heatsink on top of your CPU, you can see there in that little picture, they've got a little plate there that's connected to the CPU, which has liquid. Liquid also conducts heat very well, just like aluminium, but you need to cool that liquid down, which is why it circulates. It circulates pretty much the same as the liquid in your car's engine. So in your car's engine, you've got a radiator that has air from the front that cools down the liquid, and then it goes back into the engine, which produces the heat or gives off the heat. In this case, I suppose you can think of the CPU as your engine, which is giving off the heat, and it's got a means of cooling down that liquid. That liquid could be multiple kinds of liquid. The most common kind I've seen is normally water. Now that liquid could actually potentially also be other kinds of liquid, like ethanol coolant perhaps. It can actually be a lot of coolants. Alright guys, so let's take a bit of a look at the actual CPU installation on the motherboard. So we've already talked about when you go buy your CPU, that's probably the first thing you're going to do is you're just going to go and choose a CPU of your choice. So if I want to go and buy myself an i7, I'm going to go look at which one fits my pocket, which one's got the right clock speed, the right amount of cache, and all that kinds of gizmos, which one's got the right amount of cores, the right amount of hyperthreading. And once you've decided on your CPU, you're going to go get yourself a motherboard. And once you've got the motherboard, now all that's left to do is to install that CPU chip onto the motherboard. So you can see here the first point is make sure the processor matches the type of socket. Now obviously if you're going to go and buy that yourself, you probably would have made sure of that. So if you go buy a CPU, normally on the box of the CPU, it says what socket it is. It might say socket 1155 for argument's sake. So now what you need to go and do is when you go to the computer store or you buy this online, you need to go look for a motherboard that says socket 1155. Obviously the socket will vary. I'm just using 1155 as an example in this case. Make sure the socket is the same size. Make sure the FSB is the same speed as well. That's the front side bus. Now when upgrading the CPU, check that the new model is supported by the motherboard. That is the FSB I was talking about. So just because the pin socket is the same does not mean that motherboard can handle that CPU. It might be a matter of that CPU will physically fit onto the motherboard, but the CPU might be very well too fast for that motherboard. Then what? So make sure the motherboard can actually handle the speed of that CPU in a nutshell. They mention on a processor pin 1 may be indicated with blah blah blah. So what you will notice is, and I did talk about this previously in one of the other modules, is if you're about to go and put a CPU onto the motherboard, even if you know that's the right socket, you know for a fact it's the right socket, do not just go and drop the CPU into that socket. It can only go in one way. There's many ways you can establish whether it's the correct way or not. So my suggestion would be put the motherboard flat on a piece of table, perhaps, and then the CPU, have it in your hands and hover it over the slot. So if you hover it over the slot, you can actually see the correct way to go and put it in. So you'll find on the edge of the CPU, it's got like little holes in it. And that's going to align or correspond with like small little pieces of plastic that's sticking out on the sides of that slot where it needs to slide into. It can only go in one way. You'll also notice that on the CPU itself, on the bottom, there's a pin missing. Sometimes 3 pins missing, but there's normally at least 1 pin missing on the bottom of that CPU. And if you check on the motherboard, you'll also see there's 1 contact point that's clearly missing. So that also tells you which way it needs to go into. Also, on the top of the CPU, not the bottom, on the top, where the pin is missing, there's normally in quite many cases, there's actually like a little yellow triangle showing you which side has got the missing pin. And if you check in the slot where the CPU needs to go into, there's also a little triangle or an arrow indicating where the pin is missing. So there's so many indications. The point is, you cannot just go and slide that sucker into that motherboard, even if you know it's the right socket. You need to basically go and turn it until you find that it aligns with the pins, in a nutshell. Okay, and then we have firmware. Now, in electronic systems and computing, firmware is a tangible electronic component with embedded software instructions, such as a BIOS. Now, typically, those software instructions are used to tell an electronic device how to operate. Now, pretty much as of 2013, most firmware can actually be updated. In the past, pretty much none of them could be updated, so there's still going to be many days and many devices where you're going to find the firmware just can't be updated. Whatever you get from the manufacturer, that's what you're stuck with. But now, since 2013, more and more of them can actually be updated. Typical examples of devices containing firmware are embedded systems. This would be things like traffic lights, consumer appliances, digital watches, and then also things like computers, computer peripherals, mobile phones, and digital cameras. Firmware contained in these devices provide the control program for the device. The firmware is held in non-volatile memory devices such as ROM, EPROM, or flash memory. Now remember guys, non-volatile means if power is taken away, the memory does not forget the contents. Volatile memory was the one we discussed earlier in this course, which is something like RAM, where if you plug the power out from the computer, it forgets what was in the memory. Now, changing the firmware of a device may rarely or never be done during its economic lifetime. I have, however, seen many firmware memory devices actually permanently installed and it cannot be changed after manufacture. So you're basically stuck with the firmware you have in those cases. So, like I said earlier, since 2013, more and more devices actually do allow you to go and update the firmware. But there's still going to be many cases where whatever you have is what you're stuck with. Our next topic is the computer BIOS, which is nowadays been replaced by the UEFI. Let's first explain the BIOS, since that's the older one out of the two. The word BIOS stands for Basic Input Output System, for those that's curious. That's not actually something you need to know, just thought I'd mention it since it's a fun fact, you never know. The BIOS is basically your PC's most important startup program. It's the built-in core processor software responsible for booting up your system. It's typically embedded into your computer as a motherboard chip. To access the BIOS varies from PC to PC, but in most cases it involves pressing either the delete key or the F2 key on your keyboard a few times at the startup. So literally just as you press the power button on your computer, you've got like 1 second, 2 seconds to press the F key or the delete key a few times to get the BIOS to pop up or to be able to go into the BIOS. Now there are cases I've seen where actually both of the keys would work. It depends on motherboard and manufacturer. And another way to know is normally for like a split second on the screen, you'll actually see a little message that displays there. It says press F2 or press delete. So it actually tells you which key to go and press. Once you get into the BIOS, there you can configure all kinds of system related things. One of the most common things we configure there is the PC's boot order, a topic we're actually going to get to in a moment. In other words, what device your computer should look an operating system on for first. So in other words, when your computer boots, it doesn't know where your operating system is, which is probably going to be Windows. So the boot order tells it where it needs to go and look first. Is it going to go look in the DVD-ROM? It might be a DVD. Is it going to go look in the USB port for a potential flash drive? Is it going to look on a hard drive? So it basically just tells it where to go and look first. And if it doesn't find it there, where to go and look secondly and where to go and look third. Now regarding the UEFI, which is the newer one out of these two, pretty much any computer you buy nowadays will have a UEFI instead of the good old-fashioned BIOS we used to have. With the BIOS, you could only use your keyboard. It was normally either black or blue to screen, and the options were somewhat limited basically. Now the new UEFI usually has a nice little GUI, in other words graphical user interface, which basically means you can go and use your mouse to go and click on nice little icons. You can go and configure way more than what you can go and do in the good old-fashioned BIOS. Now the word UEFI stands for Unified Extensible Firmware Interface. It does the same job as the BIOS. Obviously, it can just do a lot more, but with one basic difference. Well, one other than the GUI fact, obviously. The UEFI stores all data about initialization and startup in a .EFI file instead of storing it on the firmware. This little file is stored on a special partition called the EFI system partition. or ESP for short, for those of you that know that. This is obviously now on the hard drive or hard disk drive. This special ESP partition on the hard disk also happens to actually contain the bootloader, just so you know. Alrighty, and then we have our next topic being boot options. We technically already indirectly covered this to a certain degree if you think about it, but anyway, this is basically the order in which the computer will go and look for a bootable device. The bootable device is usually in most cases going to be the hard drive which has the operating system installed. But there are times when you might want to format that hard drive and reinstall the operating system. Now, obviously, if you're going to wipe the hard drive, you can't run the operating system from it. And at that time, how are you going to wipe the hard drive? You need to boot from something. And that is where a secondary boot device would come in handy, something like a flash drive, maybe booting from a network device, something in that regard. So this used to always be a DVD where you would go and boot from, in the old days. If you want to go and wipe your Windows, you'll probably go and boot from a DVD. Nowadays, it's more common to actually see people boot from a USB stick, which I suppose some of you guys will just call a flash drive. This is when someone puts an operating system like Windows onto a flash drive. Or I suppose you can call it memory stick. It's the same thing, just a different word. They didn't just boot from this flash drive instead of the hard drive, so that they can go and erase the hard drive. So if you boot from the flash drive, you can go and erase the hard drive because the hard drive's operating system is no longer in use. You cannot go and delete something while it's in use. That includes the operating system, which is why you need to boot from someplace else, like a flash drive in this case, or even a DVD. Once the new operating system is installed, you just change the boot order back to the hard drive, which is normally the main or first bootable device on most computers. So what the PC does in a nutshell, it looks on the first device in the boot list for the operating system, which is usually where it will find it. It's usually the hard drive, like we said. If for some weird reason, though, it does not find the operating system on that device, whatever it might be, this device, it will then proceed to go and look on the second device, which is listed in the boot order. And then just repeat the whole process until it eventually, hopefully, finds an operating system. If it goes through the whole list without once finding a bootable operating system, it will usually then display a black screen with an error on the screen, and that says something along the lines of no bootable device. So here's a picture for you guys. This simply just means it cannot find an operating system to boot with. This can be for many reasons. One reason could be that maybe this is just a blank hard drive. It might be a brand spanking new machine and you just haven't installed anything and you just happen to have nothing plugged in or slid in anywhere. It could just be that. Or if you know for a fact that on this PC there is a Windows installed or some sort of operating system installed on the hard drive is plugged in and it is listed in the boot order, and yet you still get that message. Now that is bad because that's normally an indication that that hard drive has failed. It either has just failed or it's about to fail. Normally it has already failed. So it's a bad sign. You don't want to see that on a working hard drive that's got Windows already installed on it. That's bad. Alright everyone, our next topic on the list is PSU, or better known as Power Supply Unit. If you go and open pretty much any desktop PC, not laptop, desktop PC, you'll find this sucker somewhere there in your chassis or your case. Some of them might have a big ass fan like that that points down toward the motherboard, but the majority of them will just have a small fan that's pointing towards the outside of the case. Now that is obviously where you go and plug in the power cord to your PC, providing your machine with power. Now in this picture you guys can see it only has like one little hole for one cable you can go and plug in. Some power supplies, which is somewhat rare, have two little plugs there. One is a male plug, the other one is a female. Now if you go check on that power supply in the picture, that has got the male port. Some of them will have a male port and a female port. Now the female port back in the day was used to go and plug a secondary cable in, which will go generally to something like your monitor or your screen. Now we don't really get those anymore, so nowadays you'll go and get yourself a dedicated cord for your screen, which you'll go and plug into its own little outlet for the most part. So if you ever find a power supply that's got two little outlets there, it's simply just because the second one is to go and plug a cord in. Kettle cord is what we call them, and you can go and plug that sucker into your monitor. That's actually all it is. I would say about more than half of power supplies has like a little switch there at the back, kind of like the red one you guys see there. Although from my experience, most of them will normally be black in color, but color doesn't matter. That is to turn the power off there. So even though it's got a power cable plugged in, the PC itself on the inside does not receive any power. So if you ever find yourself needing to go and do that, that's one place you can actually go and turn the power off. Another switch you may or may not see at the back, it depends from power supply to power supply, it's got nothing to do with the price, is a voltage switch. So some power supplies allow you to go and switch between voltages. This depends on what country you're in. Some countries run on volts like 110, 120 volts, where some other countries might run on 220 to 240 volts. So depending on which country you're in, you might either run on the one or the other. So otherwise your PC is not going to receive enough power, or it's going to receive too much power, which is bad. You can see here's a list of some of the components that a power supply contains. Transformers, which obviously brings voltage down, filters, regulators, fans, it might even have a few resistors and all of that in there. So that's pretty much what a power supply consists of. A golden rule about power supplies, though, and this is not really part of this specific topic, is try not to open them. Unless you're a qualified electrician that knows what you're doing, do not open them. I actually want to go so far as to say that even if you are an electrician, it might not be worth it to go and open it, because these power supplies are so darn gosh cheap. It really is not worth the effort to go and open one if it's faulty. They cost you nothing. They're almost free. So if something is faulty in a power supply, you want to throw it away. The only time you might want to consider opening it is if you know what you're doing, you're a qualified electrician, and if it's a gaming power supply, because those ones are quite pricey. But if it's an average desktop power supply, don't open it. It's not worth it. Just get yourself a new one. Here's another picture for you guys. So the picture on the left, that's pretty much what it would look like from the outside of your system chassis. You can see it only has like one little plug. The picture on the right, that is what I was talking about, two plugs. One is a male, one is a female. The top one is where you provide power to your PC, for your PC itself. The bottom one is basically an outlet to provide power to something like a monitor. It's not compulsory that you actually plug the monitor in there. You can obviously still just go plug the monitor into its own little power if you want to go and do that. And right between those two plugs, you'll find there's like a little switch there. It's so small you can hardly see it. There, you get to switch between voltages. Not all power supplies have two plugs. Not all power supplies have that little voltage switch. And not all power supplies have a switch at the back that allows you to turn it on and off. Alright, so let's talk about power rating regarding the power supply. The maximum power output available from a PC power supply measured in watts, calculated as voltage multiplied by current. Now, what you want to know here is if you're going to go and build yourself a PC, you can't just go and throw in any power supply in there, because that power supply needs to be big enough in watts. Otherwise, if you're going to start that PC up, it's not going to start at all, or if it starts up, it's going to just restart and go into an endless loop, because your components, your hardware inside of that chassis is pulling too much power in the form of watts. So to avoid that from happening, you want to go and do some math there. So they've given us some indications here, although that I find is very inaccurate. They say a desktop PC typically 200 to 300 watts. That is if it's a very, very cheap PC with basically just Word installed on and all that. The average power supply I've seen in the local computer stores these days, the cheapest ones, the smallest ones, comes out of 400 to 450 watts. So that's what the average PC uses these days. So I would say a normal desktop PC that you go and build or buy is probably going to be about 400 to 450 watts. A gaming PC, they used to be up to 1,200 watts at some point. That was about 10 years ago. So people would brag about how many watts their power supply is. And the fact of the matter is, the more watts it is, the more power it uses. Your power bill or electric bill would be insane. Nowadays, graphics cards and all that, which is obviously the components that pulls the most power, they give more performance, but for less power. So those geniuses that make that hardware, you got to give them, a hats off for that, because they're able to get more performance out of something for less power. It's kind of like these fancy cars these days that can give you more miles or kilometers per gallon or per liter, and they give you more performance, but all for less fuel. It's just amazing. So if you go look at those engineers, I think they deserve a round of applause. So yeah, average desktop PC I would say is about 350. I actually want to say 400 to 450 watts. Gaming power supplies will probably be about 500. That's still actually pretty accurate. So 500 and up. 500, 550, that should be sufficient for a gaming, rig. The bigger the graphics card, the more watts you want, and the more hard drives you've got, and the more fans you've got in your case. And also, if you've got a few fancy lights and stuff, then you might want to go and increase that to maybe 600, 650 watts or even more. Now, what you guys will find is if you go and buy yourself a power supply, or if you just go and open a case of a power supply, it's what they call rails. One rail has got a bunch of connectors on it. It'll have maybe 2 or 3 little connectors for hard drives and CD-ROMs, DVD-ROMs on it. It could be the old Molexes, the old white ones, or the new black ones, which is for SATA hard drives and SATA DVD-ROMs. So let's say there's 3 on a rail. There's, if you don't look at one of those wires, it's got 3 connectors on it. You do not want to exceed a certain wattage on that rail. So each rail has got a certain amount of amps it supports and a certain amount of wattages. So if you suspect you might have gone over the limit, or if you're near the limit for one rail, you preferably want to go and use a different rail for the new device you want to go and install, even though you might possibly still have some connectors open on the old previous rail. So if you go look at the cheaper power supplies that has about 300 watts, 400 watts, they only have like 2 rails maybe. And if you go look at your gaming power supplies, they have 3 rails, 4 rails, 5 rails, and all kinds of special extra connectors that you'll find besides the ones that plugs into your motherboard. Here's an example of one of those connectors. So this connector is the big connector that's going to be plugging into your motherboard. All motherboards need that connector. So it doesn't matter if you've got a fancy power supply or not, if it's cheap or expensive, doesn't matter what motherboard you have, as long as it's a desktop PC on your power supply, on one of those rails, you will find this big connector that plugs into the motherboard. It's normally a 24-pin connector. And in the old days, I want to say 15, 20 years ago, it used to be only 20 pins. And then at some point in time, you'd find power supplies started coming out with 20 pins with a 4-pin extra one, which you could, detach. If you look at the bottom picture there's actually 2 pictures there. You'll find it's got 2 little clips on it. So even though it's not possible to see it in this picture, that one is most likely one that's detachable. So the 4 pins on the left-hand side can probably detach from the other 20 pins on the right-hand side. So you can actually split it. So if you have a very old motherboard, which is very unlikely, you can actually detach that extra 4 pins on the left-hand side and only plug in the 20 pins into that old motherboard. So if you have an old PC that's got a power supply that's blown, you can at least go and use some of the newer power supplies and still plug it into that old motherboard, because you can detach the 4 extra pins you don't need. But the newer motherboards these days, they've got more goodies on them. They need more power. They're more power hungry. So that is why they need 24 pins versus the conventional 20 pins we used to have. Here are some of those basic connectors I spoke of earlier that you'll find on those rails. So those rails, that's got about 2 or 3 connectors per rail, will have either just the one on the left, that's the SATA power connector, or they'll have either just the one on the right, which is the old PATA, not SATA, PATA for parallel ATA, that we refer to those as Molexes. If you go buy yourself an average power supply, they'll actually have a mix of both, maybe 1 or 2 black ones, 1 or 2 white ones. But the gaming rigs these days pretty much come out with just the black ones. They're fancy. Here are some extra power connectors that you may or may not see. Now these ones are normally for extra things like graphics cards and stuff. So if you go buy yourself a normal power supply, the cheapest kind you can find, they will probably not have these pins on them. You're going to find one that's got like 4 extra pins just dangling around. That's normally one that connects directly to your motherboard, besides the other 24 that we were talking about. That 4 one, we call it the P4, connects normally directly next to your CPU. So it's between the CPU and the back of the case in most cases, but it could generally actually be anywhere around the CPU vicinity. These two that we've got on the screen are not something you'll find necessarily on any power supply. These are normally on the more expensive power supplies like gaming rig power supplies, the ones that's 500 watts and more. You plug these into your graphics card directly as extra power. Some gaming graphics cards actually need so much power that they can't get enough from the motherboard. So even though the motherboard provides the card of power, it doesn't get enough from the motherboard, and your power supply needs to provide it with additional power that you plug directly into the graphics card. I mean, how cool is that? You're actually getting less and less of this nowadays. Like I said earlier, these developers and these guys that make these cards have been able to get more performance out of these cards and yet use less power. So even though you've got these connectors, you might actually find yourself not even using them nowadays. Alright, so power needs calculation. List the devices that need to have power served by the power supply. Be sure to include the following. So motherboard, you can't skip that. I mean, everything is going to plug into the motherboard. You have to have a motherboard. You have to have a CPU. You have to have some RAM. You have to have at least 1 hard drive. CD drives, which are, CD and DVD drives, that's optional. These days, PCs don't actually come out of those anymore because, well, who uses them? Nobody uses them. So I would actually say skip that. Floppy drives, if any, you're probably going to skip that. Those are pretty much extinct. Expansion cards, that'll probably be something like your graphics card. If you're a gamer or someone that does some sort of graphics arts or design, anything of that nature, you might have some sort of fancy graphics card. If you're a DJ or someone that an audio engineer, you might potentially have a sound card, maybe even have a TV card. Although those are kind of rare. I mean, people these days just go get themselves Netflix or Showmax or something like that. So I find it unlikely that someone's going to have themselves a TV card. Those are kind of getting extinct as well. But if you have any potential expansion cards in your PC, also calculate power for those. Here's some more points for you guys to look at. Determine the power requirements for each device. And the fun thing is, if you're building a brand spanking new PC, it actually indicates on the boxes of these pieces of hardware how much they use in watts. So on the CPU's box, it will tell you. On the motherboard's box, it'll tell you. On the hard drive's packaging, it'll tell you. On all of these packagings, it'll actually tell you how much they consume in watts, which makes it just so much easier to the point where you don't even need to know, a fancy calculator. You can just go and add them up, old school, and there you go. Add up the power requirements for existing total power load. So if you have any existing hardware which wasn't a machine already, that you need to go and add as well. The catch of that is if you had existing hardware, you might no longer have the packaging. It's not a deal breaker. I mean, honestly, you can actually just go type it into Google, and Google will tell you how much watts it actually consumes. So if you know the make and the model, there you go. Type it into Google, and you'll know how much watts it consumes. You don't need to be a rocket scientist to work this out. Consider adding a buffer of 20 to 50% for future power needs. Yes, that applies to anything in life. Whether you're building a PC, building a network, building a server, you always want to add a little buffer for future growth. So if my power consumption is, let's say 100, I'm making up a random number. Let's say it's 100 watts. Impossibly not going to be 100 watts, but let's say it's 100 watts. You want to go and plan for 120, 140 watts, somewhere in that vicinity, so that if you need to go and add something in the future, you don't have to go and replace the whole darn gone power supply again. That's just going to cost you more money in the long haul. You generally want to try and avoid that. All right, guys, let's take a bit of a look at client personal computers. Now, a lot of these are going to somewhat, kind of overlap with one another to a certain extent. So let's take a look at the first one there being standard thick client. Now, something you guys are going to hear in IT is the word thick client and thin client. The word thick client normally means it's a beefed up machine. It's got a lot of RAM. It's probably got a lot of processing power. And 10 to 1 even has a graphics card in it. So this will probably be something like a gaming rig or some sort of machine that's used for virtualization or high rendering. So it's a very beefed up machine is what we're saying. It's also generally a very expensive machine if it's so beefed up. Then I see them make mention of user accounts. Each user who wishes to access a Windows computer will need a logon ID referred to as user account. Now, later in this course, we are going to talk about more about user accounts, the different kinds you get. For example, you get local accounts, domain accounts, Azure domain accounts or Active Directory accounts. And you also get Microsoft accounts. Now, that one has actually changed quite a few times over the years. At some point, it used to be called Live accounts, then it was called Microsoft accounts, and then for a time, it was called Online accounts. They can't seem to make up the minds, these guys. In a nutshell, a user account, whether it be local or not, is used to prove that you are the owner to that device, or in this case, that account. That's what authentication is. It's proving that I am the owner of that account. So the fact that I know the username or the email address combined with the password is proof that I'm the owner of that device or that account. Now later on, we're also going to talk more about things like MFA, which stands for multi-factor authentication, which basically just means I need to give 2 or more forms of proof that I am in fact the owner to that specific account. Now for now, at this point in time, you guys just need to know what a user account is. So if you go and start up your Windows PC, it's probably going to be Windows. You just click on your account and you provide your password, and there you go. That account's got all your customizations and your settings and all that on it. The third one on our list for today is thin client, which is pretty much the exact opposite of the first one we had on the list, which is thick client. Thin client, for the lack of a better term, is a cheap ass PC. Pardon my French, but that is what it is. So they mention it's a business computer that relies heavily on another system, typically a server to run most of the programs, process, and service. Usually, yes, I would agree with that, but it's not always the case. A thin client is basically a PC that has just enough RAM and processing power and enough hard drive space to basically barely run Windows. You might be able to run Windows and at most maybe open something like a word processing program, maybe open Paint. You can do the bare minimum is what we're saying. So the companies I used to deal with, what they will go and do is they will go and buy their employees these thin client machines, which doesn't look a specific way. They could look like even like an exactly, physically, they could look exactly like a normal PC. But if you were to go and open one of those boxes, you'll find that it's got barely enough RAM, it's a cheap motherboard, it's got cheap CPU, everything is cheap and just barely enough. Or it could physically in dimensions actually be very small. But the point here is, physically, it does not matter how it looks. It is the actual hardware itself that matters. So when you start those pieces up, what these people would normally do is they would go and use something like remote desktop, and they would go and remote desktop to a server. Now, remote desktop is a form of remote connectivity. It's not the only way they would get this done, but it's one of the most common ways that these employees would get this done. So imagine you've got a company with 100 employees, and all 100 of them have got these thin client machines. What way they're going to do then is, in the morning when they start the pieces up, they open something called remote desktop. And on remote desktop, it effectively allows them to remote connect to a server. So they will see a desktop of icons and all kinds of stuff, but what they see is in fact not on their machine. It's actually happening somewhere else. So if they install a program, guess what? It's installing it somewhere else. If they run a program, it's technically opening it somewhere else. It just displays to their screen over the network. So if they save a program, they save a file, all of it gets saved somewhere else. It's running somewhere else. Everything is happening somewhere else. It simply just displays onto their computer over the network. So you can actually have the smallest, fittest client PC you can imagine, as long as it has enough processing power to run Windows and to connect to that server. That's it. So this is going to save you a tremendous amount of money when you've got a lot of people working for you and they can all connect to that server. So obviously that server is going to have to be very beefed up. I used to do this for a lot of my clients, and this saved that companies lots of money. I don't want to give a currency here because you guys are all from different countries. But in a nutshell, it's going to save you a tremendous amount of money, or your client a tremendous amount of money. The fourth one on the list is VDI, Virtual Desktop Infrastructure. Hosting user desktops as virtual machines on a centralized server or cloud infrastructure. That is actually very much the same as the third example I gave you guys, where everything is happening somewhere else. This could technically actually these days also be cloud, mind you. So at the time when they made this course, it wasn't really that popular, but nowadays more and more companies are still using that, but it's more in the cloud. And the name is actually somewhat changed. Instead of it being called VDI, it's called IaaS, which stands for Infrastructure as a Service. So you would essentially have a virtual machine running somewhere else. It's probably going to be running on Microsoft Server. It's basically a computer that's installed somewhere else. It's got Windows running somewhere else. Everything's happening somewhere else, which is on Microsoft Server. And you just connect using something like remote desktop to that server or that PC, which is running somewhere else in the world. It could be anywhere in the world. So it's not running on your PC, it's not running on your servers on premises, it's all happening somewhere else. That is a virtual desktop infrastructure environment. Then you've got media centers, a computer used for media streaming, often connected to surround sound speakers and capable of recording TV shows. So once again, I've said it before, some of these are going to somewhat or even completely overlap with one another. So you might find some of you guys will have a computer in your house which you use for streaming, using streaming it, gaming streaming, YouTube streaming, or just streaming movies to your house or TV series to your house, either legally or illegally. I don't want to know if it's illegally, just don't tell me. Gaming rig, that one, a computer used for standalone or online gaming. I think there's pretty much not one of you guys that doesn't do this these days. Everybody's got a gaming rig of some kind, either cheap or expensive, but you've got a gaming rig. I don't think I even need to explain what it includes. You're probably going to have some nice speakers or nice headphones, maybe even both. Potentially virtual reality goggles, VR goggles. Those used to be very expensive, but they're getting so cheap these days because of supply and demand. May use specialized gaming equipment such as gaming controllers, joysticks, gaming mouse, gaming keyboard. Not compulsory, but it obviously adds on to the fun. Then we have an HTPC. Now, on its own, that abbreviation looks very fancy and very complicated. But in reality, they're just talking about a home theater PC. So you see how simple it actually is. It looks very darn complicated, but it's simply just a home theater PC. A PC used in place of consumer appliances such as a PVR. I mean, people don't really use things like PVR anymore, people. Nowadays, and this includes myself, I've got a PC in my lounge which is connected to my TV.
So my TV is a smart TV. Pretty much everybody's TV is a smart TV these days. So it can go and connect to YouTube and Netflix and Showmax and all of that on its own. It's connected to the internet. It's connected to everything in my house. All my TVs in my house are connected to everything in my house. But then in my lounge, I've got a dedicated PC, which I suppose you can call a home theater PC. It's connected to that PC as well. And quite often I'll go and maybe, get myself a movie and I'll put it on that TV or on that PC of mine. It's an HD movie. And I'll, play it through my PC onto my TV. So you can basically say my TV is a second monitor or screen for my PC, but it's one high definition screen. That's actually what it is. So if it's great for entertainment purposes. If you want to go and play a game on your PC, you want to show your family or friends, in your household what you're playing, that's actually great for it. It's kind of like streaming on YouTube if you think about it, or streaming on Twitch. When you've got a PVR, personal video recorder, software installed on a home theater PC, the HTPC which we talked about earlier, to record and watch TV broadcast. Yeah, I don't know. People don't really do that anymore now, do they? Last one here, home server PC. Also somewhat overlaps with some of the other ones we've discussed so far. Either a home theater PC with a slightly expanded role or a repurposed desktop or low-end PC server used primarily for file storage, media streaming, and printer sharing. What a lot of people do is instead of getting themselves a PC which they use for storing their games and their movies and family photos and anything storage-wise, instead of doing that, they'll go get what they call a NAS drive. NAS. It stands for Network Attached Storage. Something we're still going to discuss later in this course, but it basically involves buying yourself something that's much cheaper than a PC. You slide hard drives into it, you plug a network cable into that device, you plug a power cable into that device, and there you go. All you need to be able to connect to that device is its IP address. So via your PC, via your phone, via your tablet, you can access that device, and you access it exactly like you would access a PC over the network. So if you are a guest in someone's house that's got a NAS drive and you connect to that NAS drive, you would basically not even know it's a NAS drive. You're going to think it's a PC you're accessing over the network. You might be copying movies and games and files from it or copying to it. None the wiser that it's actually a NAS drive. Much cheaper. And they've also got reliability into them because most of them have got RAID 1 built into them. So if you guys have been following my series, you would know what RAID is because that was discussed in our memory module, which I think was module 4 if I'm not mistaken. Alright, so since we're talking about NAS, I might as well throw it in here. Network Attached Storage. A storage device with an embedded operating system that supports typical network file access protocols. So a NAS drive, if you were to go and connect to it for the first time, if you've never worked on one, it looks very much the same as an Apple operating system. I'm not going to go so far as to say it is Apple, but it's pretty much the same as Apple. So even if you have never ever in your life worked on a NAS drive, you can figure out how to use it in a matter of less than 5 minutes. It's made that user friendly. It really is that user friendly. The IP address for a NAS drive is usually 192.168.0.1 or .1.1 at the end. It depends on manufacturer and model and all that. So you get many shapes and sizes, you get many brands. One of my personal favorite brands that I used to work with, and I'm not promoting them, is QNAP. So if you want, you can go run a search on Google for the brand QNAP. So QNAP, QNAP, and go click on images and you can go get an idea as to what they actually look like. They could be square in size and dimensions, kind of like a car battery, or they could be flat like a blade server, where you can actually slide them into a server rack. So basically they take normal desktop hard drives, not any fancy SAS drives or SCSI drives. They accept normal desktop hard drives. So if that NAS drive has got 2 bays, because they normally have equal amounts, it's normally 2 bays, 4 bays, 8 bays, 16 bays. You'll find it's always an even number. And the reason is because of the redundancy that's built into it, the RAID we spoke of. So if you've got 2 hard drive bays and you go put in 2 1 terabyte hard drives, you might think, oh, I've got 2 terabytes of storage. That's actually incorrect. In reality, you actually have 1 terabyte of storage because whatever's on the one hard drive gets mirrored, duplicated, or cloned to the second hard drive. It's a duplicate. That's where the redundancy comes into play. It's very easy to set these things up. You literally just go plug a network cable into it. You plug a power cable into it. You connect to it via, a browser, like you would connect to a router or a switch or a modem. You open a browser. You type in the device's IP address. You type in the username and the password. That obviously varies from model to model and manufacturer to manufacturer, but it generally is the username is usually admin and the password's either admin or it's blank. It is advisable, like with anything else network-wise, to always go and change that default password. So that's one of the first things you want to do. Besides changing the IP address, you want to change that password. Changing the username is optional because as long as you've changed the password, that already locks people out, obviously. Alright guys, like usual, at this point in time, you should know what to do. Smash that like button, it really does help my channel. It supports me quite greatly when you do that. And if you would like to know when Module 6 comes out or any other module in this course, or quite frankly actually any material I upload, consider subscribing, otherwise you're not going to know. Preferably with the notification bell, otherwise you also might be not going to know when I upload this content. Like usual guys, I thank you for watching this series and I hope to see you again on Module 6.
If you love me, let me know. If you don't, then let me.